We talked about ice converting to liquid water, solids converting to liquids is very common, but some solids can directly be converted to their vapor form. You are looking at a simple setup. This is some china dish which you are going to heat. You have taken some camphor on this china dish. When you heat, you expect the vapors to go up, and to trap them, you have inverted a funnel, and you have closed this by some cotton plug so that nobody can escape. Right? You can take ammonium chloride also if you want, or you can take camphor, which is commonly available on that china dish. There is a burner here which I have not shown. So you heat using that burner, and what you find? You find that in this part, which should be cool because it is at some distance from this point, there is a deposition of particles which resemble these particles. So basically the same thing is getting deposited here. How can it fly? It must have got converted into particles. You don't see liquid there. They must have got converted into particles. Particle means vapor. So this region must be rich with particles of these. And then because this is a cool region, there is a solidification taking place there. Right? This process is called sublimation, in which solid directly converts to vapor without first becoming liquid. We have talked a lot about heat and temperature, ice to liquid water, then liquid water to steam, and then this thing, camphor, sublimation. It has all about been heat, temperature change. Not temperature change always, but mostly temperature change, and when there is no temperature change, heat suddenly is there. But pressure can also play crucial role. And if you have a combination of these two, pressure and temperature, then it can be very useful to liquefy gas. In gas state, the distance between the particles is too much. The interparticle forces are very weak, right? Almost negligible. But if you can apply pressure, force the particles to come close. Distance reduces, interparticle forces can increase. Now, if you reduce temperature, it can help even further, because temperature sort of agitates the particles, and that agitation gives them higher energy to move away from each other. So if you are applying pressure, if you reduce the temperature, it can be good to bring them close. So if you do a combination of these two things, you apply pressure and you reduce temperature, then that can help a lot in bringing them close. Low temperature would mean that they don't have a lot of kinetic energy, so that they can't run away from each other easily. And high pressure means they have to come close now. So one can have this type of setup for that. This is your gas sample. This is a piston. You are going to apply force from here. That will increase the pressure in this region. Piston will come down and down and down. Less and less space will be available. Imagine piston coming here. Right now, if I can drop particles like these, just imagine what happens when piston comes somewhere here. I will have to draw those particles in very close region. So they have no choice but to come close. So gas can be liquefied. Gases can be liquefied. You may be accustomed to hearing oxygen gas, but it is possible to liquefy oxygen. It is possible to liquefy many other gases also. So while we are talking about solid to vapor conversion or liquefaction of gases, one very interesting thing should be mentioned here, and that is dry ice. Normally the ice that we use, we can't call it dry because it is bound to have some liquid water associated with it. It can't be perfectly dry. When you touch it, the heat of your body is going to certainly melt some amount of ice. Or if you just leave it open, the temperature of the room is certainly going to melt some part of it at least to begin with. So the ice that we normally use is not going to be dry. But carbon dioxide, you know, is gas, and plants during photosynthesis take it. So normally you hear carbon dioxide as gas. But we can have solid carbon dioxide stored at high pressure. It can remind you of ice. But then, when you store it at high pressure, fine. But when you reduce the pressure to the normal pressure is the pressure under which we live. Now, we don't feel it, we are accustomed to it, but why do we live under this pressure? That is because of Earth's atmosphere. Earth has got substantial atmosphere. So imagine so much gas is above us. That pushes us. So that's why we are always under some pressure. We are accustomed to it. We don't really feel it. It doesn't really trouble us. That pressure is called 1 atm pressure, 1 atmospheric pressure, 1 atm. When you see that some car tire is being filled or some bike tire is being filled, then it is filled at certain specified pressure. Next time when you see that happening, try to see the reading, what that instrument reads when such activity is going on. See also the unit it is using. There are various units for measuring pressure, and I'm talking about one particular unit called ATM. But there are several other units like Pascal, bar, centimeter mercury, millimeter mercury, and so on and so forth. So the normal pressure, the pressure at which we live, that is 1 atm pressure or 76 millimeter mercury pressure. 76 centimeters, 76 centimeter or 760 millimeter. (76 centimeter or 760 millimeter mercury pressure). That is same as 1 atm, the pressure under which we live due to the atmosphere above us. When we are talking about solid carbon dioxide, that is at high pressure. Now imagine you reduce the pressure to 1 atmosphere where you have stored that solid carbon dioxide, reduce it to 1 atm. And you will see that it will not become liquid. It will directly become vapor. Liquid not involved at all. So where is the wetness? Nothing like that, right? Ice directly becoming solid ice, dry ice directly becoming vapor. Now that's why it's called dry, by the way, because it is directly converting to vapor. So it's called dry ice. So that means this thing, due to change of pressure, is converting directly to vapor form. Otherwise, normally you will see that solid, liquid, then vapor. But this is solid directly to vapor. That means that we can play with heat, temperature and pressure and convert one state to another state suitably. By suitably choosing temperature, pressure, heat, etc., we can convert one phase to the other phase. Liquid to gas, vaporization. Gas to liquid, condensation. Liquid to solid, solidification. Solid to liquid, fusion. Solid to gas, sublimation. Gas to solid is also sublimation. Solid to gas, gas to solid. Both are sublimation. Any questions? Let me know.
So they could be compressed at a high pressure and a low temperature.
Correct. High pressure, low temperature. What's going on? Naphthalene balls disappearing with time without leaving any solid. What could it be?
Diffusion. Sublimation. Sublimation.
Sublimation. Right. What one word would you use to describe this process? Just one word.
Diffusion.
Diffusion.
Perfect. Perfect. Now, you have to tell what are these A, B, C, D, E and F. Let's begin with A. Solid to liquid conversion. What would you call it?
Fusion, sir.
Fusion is perfect. Then liquid to gas.
Sir, vaporization.
Correct. Gas to liquid.
Desiccation. Condensation.
Correct. Then liquid to solid. D.
Solidification.
Correct. E. Solid to gas.
Sublimation.
Sublimation.
Correct. Yes. Then comes gas to solid F.
Sublimation.
Sublimation.
Sublimation,
That's
sir.
it. All right. Now coming to the last part of this topic. Actually, we have touched upon it earlier, but now we will be more elaborate. And that's called evaporation. I gave several examples earlier: drying of clothes, cooler, all those things. They actually fall under evaporation. Now let's understand, why does it work? You're not making the temperature 100 degrees centigrade. So why should clothes dry? When you look at various particles, then you find that all of them are not equally energetic. All of them are not equally energetic. I'm talking about watching particles inside the liquid, and especially near the surface or on the surface. Imagine an interface between liquid. Imagine an interface between liquid and air. This is that interface. All particles of the liquid do not have the same energy level. Some have more, some have less. It is the particles that are on the surface or near to the surface that are very important, because it is easy for them to escape. Liquid particles apply forces on each other. So generally speaking, it is not easy for some particle to escape or liberate itself, because other liquid particles are applying forces on it. But consider the particles that are on the surface or are very close to the surface. And in those particles, some particles are having high energy. All particles do not have same energy. Some have more, some have less, some have average value. Focus on the ones that have got high energies. They are the ones, they should be close to the surface or on the surface. They are the ones who just jump up. Just jump up, saying goodbye to other liquid particles. They are liberated. They reach here. And then they become free, like gas, going anywhere. Gas particles go anywhere, absolutely free. That is the cause of evaporation. You're not heating, but still it is happening. Okay? So, if now I have to explain that why an earthen pot cools water, then I can use this language, that some particles of water that are high energy particles they escape. And if high energy particles are escaping, then the leftover particles, their average energy will fall down. Say there are three students, and just using some hypothetical numbers. Student A gets 100 out of 100. Student B gets maybe 80 out of 100. Student C gets maybe 70 out of 100. So what is the average of this group? Let me make it 90. What is the average of this group?
50.
Total is 240. 80 is the average, right? Now the most energetic, or the one that had most marks, that fellow leaves this group and goes somewhere else. Now in this group there are all 2. Now what is the average?
75.
75. So if high energy water particles are escaping, then the average energy of the remaining fellows goes down. And if average energy goes down, then temperature reduces. So water cools down, or surrounding cools down. So same thing can be explained in 2 different languages, and technically speaking I would prefer this language, that high energy particles are escaping, so the leftover particles have got lower energy, and therefore the temperature reduces. What's the other language which was used earlier? That language used latent heat of vaporization. So when particles come out, they absorb latent heat of vaporization, and because they absorb this energy from surrounding is cooled, temperature reduces. These are the 2 explanations. Since earlier we did not talk about this approach of high energy particles coming out, I used the other explanation. But technically I would like to use today's language, because it doesn't make use of latent heat of vaporization. Strictly speaking, latent heat of vaporization is defined at 100 degrees centigrade, and when this evaporation process is going on, when clothes are drying, or when earthen pot is doing its job, and for those cases it is nowhere near 100 degrees centigrade. So I would like to avoid to use that language. I would like to avoid it, but it is also acceptable, and that's why it was used earlier. But now you have got better understanding of evaporation concept. So why would clothes dry? Particles of water that are inside clothes, especially the high energy ones, they are jumping off. Now why won't clothes dry in case of a rainy season? Why won't they dry? Aren't high energy particles jumping in those days also? The problem is that Yes, go ahead.
So because it's the rainy season, there's a lot of moisture in the air, and there's not much space for the water particles to just jump off.
Okay, but think it this way. There is a reverse process that is also possible. Look at the drawing. When high energy particles are jumping off, they are going in this region and they are increasing and they are going randomly. They don't have a mind that they can decide that, okay, I should travel in this direction. They don't think and travel, right? They randomly go and collide. So think about this particle. It may come and collide here, right here. And the moment it collides, other water particles attract it and don't let it go back, trapped. So a reverse process also happens. As evaporation process happens, reverse process also happens. Now just imagine during rainy season what would happen. There is a lot of moisture in the air. Moisture is nothing but water content in the air. So a lot of water particles are in there in the air. So they will be colliding with clothes every now and then. So the high energy particles of the cloth will be jumping off, but cloth will be taking these particles also that are coming from the air. So it doesn't work well. So evaporation doesn't require boiling point. Now what factors influence evaporation? Let's see. You must have seen, or probably would have been told also, that if you want to dry the clothes, spread them. Isn't it? When you spread the clothes, they dry better. So technically we would say increase in the surface area. We know that evaporation is a surface phenomenon. Particles on the surface or particles close to the surface. So it has to be better if surface area is more. So on what factors does evaporation depend? One factor is the surface area. Larger the surface area, better the evaporation. Point number 2, while you don't need boiling point, temperature helps, because temperature will increase the kinetic energy. And higher kinetic energy means it is easier to escape. So higher temperature would help in evaporation. Then moisture should be less. Reverse process should be less. Humidity or moisture, that should be less. That will reduce the reverse process taking place, right? So that is the third point. Then fourth point. Again, it's a practical observation that if it is high wind situation or a fan situation, you probably would have noticed that sometimes if people are to dry clothes in the night, then the fan is switched on. So that helps in drying the clothes. Now why does it work? Why does it work? Imagine that I have got high energy particles escaping and coming here. They have escaped and they have come here. I don't want them to go back. I put a fan here and I blow them away. Isn't that great? No chance of them going back or others going back. No chance of them going back or others going back. Air may have moisture already, humidity already. So those particles going back, blown away, not able to go back. So whatever we find practically or experimentally, we have explanation for all of those things theoretically. Increase the area, surface area, increase temperature, decrease moisture, increase the wind speed if you want to help the evaporation process.
Sir, does the wind blow some of the water particles also?
Can you repeat? Does the wind blow some water particles also, is what you said, I suppose?
Sir.
You mean liquid? Water particles that are inside the liquid? That's hard. That's difficult.
So I think what he tries to mean is that there are particles on the surface which also get blown away by the wind.
You see, the particles which are on the surface and that are in contact with other water particles, they are not easy to be removed, unless they have got themselves high kinetic energy. If you want to remove them by wind, it has to be really strong wind. So generally when we talk about wind, under normal circumstances of wind speed, etc., then we talk about wind blowing those water particles that have already left the water surface and come out. Acetone is there in nail polish remover. So at least one of them you would have tried, hopefully. Or if not, you can add alcohol also, or spirit. That's your assignment question. We stop now.